Fluorescence anisotropy is a method scientists use to study molecules and how they interact with one another. It makes use of linearly polarized light that is allowed to be incident upon a sample of fluorescent material and studies the emission from the fluorescent material after it relaxes. Through the data, you can tell things about the molecules like their size, the way that they bounce around during Brownian motion, and whether or not they combine to one another. Anisotropy is defined as the property of substances to exhibit variations in physical properties along different molecular axes. Basically, it's directional dependence on a molecular level. Fluorescence theory states that fluorescent materials, when a laser or some other energy source is incident on them, move to an excited state for a few picoseconds, then relax back to a ground state via internal conversion, vibrational relaxation, and eventually an emission of the photon. So the key to fluorescence anisotropy is the vibrational aspect of the relaxation. The Brownian motion caused by the fluorescent relaxation can be measured by restricting the dependence of the excited molecules via linear polarization, and then measuring the directional dependence of the emission. Each molecule floating around our sample has its own random directional dependency. The probability that any given molecule will be excited by a light source incident upon it is related to the directional dependence of the light source, as well as the directional dependence of the molecule. For an untouched light source, this will cause all the molecules present to become excited, as there would be waveforms of all degrees within the beam. However, our beam is linearly polarized when it is incident upon the sample, meaning that there would only be one angle of light waves that it oscillates on. Because of this, only the molecules with a similar angle would become excited by our beam. After the molecules excite, they begin the relaxation process. After dropping energy via internal conversion, the excited molecules will start to move. This movement is random, but through the jostling around the molecules will rotate and change the angle from the angle that the polarized light that was incident upon it had. After the molecular movement, the rotated molecules will relax to the ground state and emit their light. Each emission from each molecule will itself be directionally dependent, and by measuring how much light remains oscillating in the same direction it was initially polarized in, and comparing it to how much oscillates perpendicularly to the initial polarization, we can tell how much movement occurred, or whether movement occurred at all. So once we have that data, we can learn a few things about the molecules. We can broadly determine the molecular movement of whatever we're studying based on how much it moves. We can also determine the size of the molecule. Larger molecules will rotate more slowly. So by binding fluorescent materials to different molecules and comparing the anisotropy of each, we can tell which one's larger. We can also tell whether or not molecules bind with each other by comparing anisotropy values before and after attempting to bind. This is what we'll be using our setup for now that it's complete, and it's useful because a lot of how our body operates at the molecular level has to do with protein bindings. For instance, by seeing which antibodies bind to certain proteins, fluorescence anisotropy can tell us whether a medicine will or will not be viable for use. The change of equipment from a continuous laser to a pulsed laser allows us to study a few more things, most notably by making use of a technique called fluorescence lifetime imaging microscopy, or FLIM. A continuous laser leaves no time for the fluorescent material to relax, meaning the output is viewed as a continuous value. Whereas by using a pulse laser, we give the fluorescent material time to relax between each pulse, causing an exponential decay for the output. The decay pattern lets us measure how long the fluorescent lasts, which is useful for monitoring microenvironmental parameters like temperature, viscosity, pH, and ion concentration without harming whatever subject we're studying. So the system itself begins with a 477.6 nanometer pulsed laser emitting pulses rapidly. It is then through a couple alignment mirrors directed to be incident upon the sample, which rests in our objective lens. The photons from the sample that is caused by the relaxation of the fluorescent material are emitted, and then through more alignment mirrors are incident upon a linearly selective beam splitter, and it allows the vertically selected light to transmit through, and it reflects the horizontally selected light. The vertically selected light from the emission and the horizontally selected light are guided into two different avalanche photodiodes, which basically allow us to determine the intensity of each. The mathematical model for analyzing fluorescence anisotropy is the ratio of parallel intensity to perpendicular intensity, which is normalized by the total fluorescent intensity.